Hi, and welcome back to the Cisco CCNP route training from TrainSignal. Again, my name is Joe, and I'm your instructor. We're actually going to be dealing now with route redistribution. Very seldom do you have the opportunity to have one single routing protocol running throughout your enterprise for a variety of reasons. So we're going to look at what it takes to redistribute protocols into one another. In this particular lesson, the topics we'll be concentrating on are planning and design for redistribution, and then how to configure redistribution. One of the things about sharing information between routing protocols is because they don't always measure things the same way, it's important to be able to approach it with an intentionality. In order to be able to plan and design the system, the outcomes are a little more certain. So we're going to look first at why in the world you'd ever want to use redistribution to begin with, because honestly it could be a pain. Understanding the principles regarding route redistribution. Some potential issues, because as you might guess, there are certain things that you have to pay attention to. Planning for optimal redistribution, then finally just some design principles to bring a sense of sanity to this entire process. So why would you want to use redistribution? Ideally, you use one protocol throughout the enterprise. It behaves the same way everywhere, and it's not that complicated. However, there are actually reasons for that. Some are business related, and some are technically related. The business decisions and the technical decisions frequently are in often separate parts of the organization, but it's important to understand the aspects of each. So business reasons. You can see the graphic to the left, just kind of what we're talking about, being able to take care of redistribution. But it could be merger and acquisition. I've worked with a number of companies in my career that have acquired other companies. There are, for instance, in the banking industry, it's very common for larger banks to acquire smaller banks, and I've dealt with the repercussions of that. And frequently, when one organization acquires another, everything is not exactly the same. They could have different versions of routing protocols, different versions of software on the desktop. I ran into one banking system where one was using one version of Cisco Unified Communications Manager in the 4.x range, which is extremely old at this point. And the other organization, the acquiring organization, actually had a much newer version. There was an entire conversion process that happened regarding that. So frequently, environments are not identical. There are very different topologies. They may use completely separate service providers. They may also use completely different hardware vendors, Cisco partners and such. The routing protocols can be different. And because most enterprises default to using private addressing, there may be overlap with that. And the strategy that's being used with that could be completely different. And frequently, the assimilation process of one organization taking over another, it requires a transition plan. Very seldom is it simple enough to just be able to have some very quick changes to be able to take care of everything. There's usually an intentionality and a plan that's required for it to work well. Another reason that you may have to use redistribution is not because of the acquisition, but just simply because of separate divisions or subsidiaries. Some large holding companies can own a number of other companies or have separate divisions and things like that. So there are reasons why you might have different routing protocols in some of these semi-autonomous divisions. There might be very autonomous divisions or groups. I've worked for organizations that were very regionalized and everything was very independent in feel and operation. There could be a joint venture where two companies actually own another company that they're operating together, but it's essentially a separate company. There may be political considerations why one part of the network is operating entirely different from another, and there could be compliance or regulation issues. But these are all things that are related to something within a business entity that may have different, essentially, islands of networking. It could be a matter of connectivity between partners. Now, this is not a situation where networks are actually joined, but there's a sense of wanting to maintain a boundary of trust. In the old Windows NT world, you had trusted and untrusted networks. Well, in this case, they may not be legally bound to one another. They may not be merged in their networks, but they do require connectivity. And I've worked in situations where there's been connectivity required between organizations, and that routing protocol might be different, the one they're using between each other, than what might be running in the enterprise. And then typically with that, there's restricted access involved. So much for the business reasons. They're pretty straightforward. The technical reasons can actually be a little bit deeper and more complex. To begin with, there may be legacy environments. There may be some devices in the network that are still there, still operating, haven't been taken out, that don't support newer protocols. Not exactly an everyday thing, but it does happen. I've done a number of network assessments over the years where there are devices that would be considered vintage. In fact, I would use the word museum quality rather than old stuff that needs to be ripped out. But the point is there, it might not support some of the newer things. And there may be older equipment that's still in the network that is being phased out, but it's not there yet. Another technical reason is multi-vendor networks. If you have routing devices within the enterprise that are not Cisco, EIGRP is going to be a much more difficult sell. So the inability to be able to support EIGRP, and you end up needing to use OSPF or something similar. Another reason from a technical standpoint for route redistribution has to do with multi-vendor networks. If, for example, it's not an all Cisco environment, then you're going to have a difficulty really being able to use a single protocol, for instance, like EIGRP. You'll have to either default to OSPF or something that's more industry standard, or you'll have to do something extremely creative. And many times when you acquire a company or companies, this is not the business side but the technical side, is there's maybe all kinds of equipment that gets inherited, and it may be phased out over time, but you have to deal with it for some period of time. Another technical reason is data center environments. There may be just a need for a very restricted, tight protocol within, for instance, the data center, and or even within the enterprise. The headquarters location may, for instance, all run EIGRP, but elsewhere it might be different. Frequently, when you're using MPLS WAN type circuits and services, you may have a limitation on the protocols that are available to you. For instance, you may have one certain IGP within the headquarters. We talked about a moment ago. Let's say it's EIGRP. But connectivity to their service providers may require something else. For instance, many times service providers will either use a sort of static connectivity where essentially you build the routes invisibly in the cloud, so to speak, or it's BGP. Very seldom is, at least in my experience when I've worked with different providers, has it been the ability to be able to use an IGP between the customer edge and the provider edge. It does happen, but it's just not there as often. You also may be transitioning from another protocol. In larger networks, for example, the topology may be changing. The core routing protocol may be changing. Or it could just be simply a matter of static routes have been used for a very long time, and transitioning to a routing protocol certainly requires some extra work. So in that case, being able to use a phased approach, a sensibly phased approach, can make continuity and a smooth transition that much easier. So let's now move from the why you would use redistribution to a little bit of the requirements and background. Ultimately, you have to have at least 2 routing protocols or routing domains. For instance, on the graphic to the left, we have 3 of them listed. We have EIGRP on the left, which is the one part of our lab. We have OSPF on the right. And essentially, they can't communicate without some translation between these 2 protocols and sharing of the routes. Now, we also have within the network, and essentially bridging those 2 sections together, is BGP. So this actually makes the environment quite a bit more complex. But things you might not consider as protocols per se are things like static routes. Static routes are not a protocol per se, but yet if you bring them into a dynamic routing protocol, it's considered redistribution. So those 2 protocols, either, in this case, EIGRP, OSPF, or static and OSPF and so forth and so on, you have to have at least 2 protocols or domains involved. The other thing you're actually going to need is 1 or more functional links between the domains and essentially devices. Now, we simply just have 2 devices linking this together, router 1 and router 6, and we have a single link, which just makes things that much simpler. Best practice usually specifies having more than 1 link between those kinds of devices, and possibly actually separate sets of devices. So you may have, instead of just 1 router in the OSPF domain and 1 router in the EIGRP domain, is actually having 2. And it certainly creates more complexity, but that's one of those things. The actual hard requirements is at least 1 functional link. Now, the purposes for redistributing routing information is essentially 2 or more routing sources sharing real-time network reachability information. And you can actually do this in 1 of 2 ways. You can do one-way redistribution, where routes from one protocol are being redistributed into another, but not necessarily the other direction. You may just rely on a static route or something like that. Or you're actually sharing routes both directions, which is called mutual redistribution. And when you have mutual redistribution and mutual redistribution points, not just one device but several, it can actually become very complex. One of the things to keep in mind in this is that each protocol has a different way of measuring reachability. They have different criteria, different metrics for selection. OSPF, for example, as we talked about before, it's cumulative cost. All the costs from one device to a destination network, all those costs are added together to express the metric. RIP just simply uses hop count. Whether it's version 1, version 2, it's simply hop count. EIGRP uses bandwidth and delay, and BGP doesn't use metrics per se, but actually a complex set of path attributes. So obviously, sharing routes between them, you have to finesse things a little bit in order for there to be able to be some sensibility in sharing the information. To redistribute, you have several tools available. One, probably the most obvious, is under the routing protocol process. You can just do some simple redistribution with just the redistribute and then the keyword, and there are actually several. You redistribute connected, static, metric, because you can set the metric, route map. Obviously, when we start looking at specific protocols, OSPF, RIP, BGP, EIGRP, but there are a number of others as well, even some very sort of ancient protocols that you might find. One of the easiest ways to do this is go into a device, put a routing process in place or log into a routing process, and then do redistribute and then question mark and actually see all of the different options that are available. Another tool for redistribution is changing the administrative distance, which under the routing protocol you use the distance command. You can actually change it per route for everything that's imported from a particular source and so forth. Another important thing is default metrics. Not every protocol requires a default metric. It may just calculate one on its own. OSPF and BGP, for example, can do that. However, in RIP and EIGRP, if you have not configured a default metric, the routes will not redistribute. So that's really important to remember. OSPF, on the other hand, you can specify a default metric, but OSPF will automatically assign a metric of 1 for BGP learned routes and 20 for anything else. You can configure using the redistribute command with a metric subcommand keyword, or you can use a route map, which we'll talk a little bit about later. Another redistribution tool is access list. You can actually specify routes to permit or route to deny. This is, again, a form of filtering. And these can be paired with distribute lists, route maps, and other tools. An additional bit of help is route tags. RIP has a 16-bit wide tag, and EIGRP and OSPF can use 32-bit tags. But it's something you can actually do when a route's redistributed. You can actually tag it with a value, and then if you have to do something with it later, you can actually reference the tag. Route maps can actually be very helpful with redistribution. You can selectively match routes by, for example, IP address using access lists or even prefix lists, BGP communities, AS path, the OSPF route type, internal, external, so forth, tags, and so forth. Route maps can also not just match, but it can also alter route criteria, as we saw when we were working with our BGP part of our lab. We did AS path prepending, and we actually set the weight for a particular attribute. So AS path, BGP community, OSPF route type, the BGP origin code, you can actually change the incomplete to internal, IGP, and EGP, and so forth. You can also set tags and metric values. Redistribution into the EIGRP protocol, pretty straightforward, but we want to step through basically the process. And here, for instance, the syntax is redistribute. In this case, it'd be what's the other protocol. Again, remember, static, connected, OSPF, BGP, and so forth. Then the metric value, you can actually have a default metric value defined, or you can actually define it here, metric, and then the different aspects of that. Match for the criteria. This is more OSPF specific if they are being redistributed, like what types of routes. Then the tag, if there are tags involved, or route map can be referenced. And just a little bit of secret decoder ring type of explanations here is the protocol is obviously the source from which you are importing those routes. The metric is specifically the EIGRP metric to use. We'll define that a little bit more closely in a minute. Match is, if you're using OSPF, the OSPF route type to use. Remember, internal, external, and so forth. Tag will tag the routes, and route maps will actually obviously allow you to specify criteria, as we talked about previously. If you're redistributing into OSPF, similar syntax, but if you're redistributing EIGRP, for example, you have to specify the autonomous system number. If it's BGP, the same way. If it's another OSPF process, you have to specify the process ID, and some of the other aspects of this we just went over. So it's protocol metric, which is optional. You don't have to set the metric. It'll do it automatically. Metric type, do you want to have the route imported as an E2, which is the default, or E1? Remember, E2 is just basically the external metric being pulled into OSPF. E1 also includes the cost to get to the autonomous system boundary router. Match, you would use match if you're trying to import from another OSPF process. And the word subnets there is critical, because if you don't have the word subnets in there, it's only going to import major network numbers, which is the cause of many troubleshooting efforts regarding routes not existing in the table. You can also include tag for tagging routes, route maps, and I already harped enough on the subnets keyword. Redistribution into BGP, much shorter syntax. So you have the redistribute command and the various aspects, protocol, redistribution source. The metric for BGP, remember, this will be reported as the multi-exit discriminator value. Match if you're matching an OSPF type, and then route map, much shorter list of criteria. So let's talk a little bit about potential problems or issues with redistribution, because when you're bringing routes in from another process, all kinds of interesting and squirrely things can happen. So routing loops can happen with multiple redistribution points or domains. Remember, if it's just 2 routers like we have in our lab, it's pretty straightforward, although technically, since there are 3 routing domains, multiple routing domains, all kinds of things that can happen. So one of the things that can be problematic is you import routes from another protocol, and then you end up advertising them back to that protocol inadvertently, and that can create all sorts of routing havoc, loops, and all sorts of other things. It can also result in suboptimal routing. This is particularly true in the way we have our lab set up, because OSPF and EIGRP are being injected into the BGP domain by redistribution, and then conversely it could be re-advertised back because there's essentially a protocol sandwiched in between the other two. So there's a couple tools for doing this, preventing this, that is. First, you can specify higher IGP metrics. So in other words, redistributed routes into OSPF, you can actually create a much higher metric to make sure that if it is advertised back, it's not going to affect the routing table. You can also change administrative distances, particularly if there are a number of things running on one particular router, such as those that are doing the redistribution. You can tag the redistributed routes. So when the tag is recognized, essentially you can have the routing process ignore them. And then more often than not, one of the things you're going to end up doing is filtering routes as they come back into the domain. If you know what routes you're looking for, you can either allow specific ones or deny the ones you want to make sure don't end up being re-advertised back into the process. So when redistributed routes aren't showing up, what are just some common causes? Well, remember in EIGRP specifically, we're going to look at that first, the metric or the default metric has to be configured. Now, if you haven't done either, things aren't going to show up. If you don't configure a default metric, but you use the metric keyword when you're redistributing, you'll be okay, and vice versa as well. But when you define the EIGRP metric, you have to specify all 5 metric elements: the bandwidth, delay, reliability load, and MTU. I think it's best practice if you go ahead and define a default metric, and then if you want to change it for certain routes, you can do that in the redistribute command. But if you try to configure a metric and you leave elements out, it's not going to accept it. You'll get basically an error message saying, incomplete command. So keep that in mind. Always make sure in EIGRP you've defined a metric and make sure you use all 5 elements. I just have some default values here that I just selected as one way of being able to use the values. When you're redistributing to OSPF, you don't have to define a metric or default metric because it'll happen automatically, as we talked about before. It's probably recommended. Gives you more granular control. So we already talked about the defaults. The metric for BGP being redistributed into OSPF is going to be 1, 20 for everything else. All routes will be imported as E2 routes. Unless it's an NSSA area, then it'll be N2 routes. But the point is that it will create an external route with a type 5 LSA for each route. And again, the greatest problem is forgetting to specify the subnet's keyword. Now, if you just do redistribute OSPF and you just enter it, it'll say only classful networks will be redistributed, and that's usually your clue. Then you just back out of that command and re-enter it. But make sure you specify the subnet's keyword. Redistributing into BGP, again, default metric not recommended. It'll just pull in the IGP metric actually. But keep in mind that it's optional but recommended. And when you're specifically importing OSPF routes, you can actually specify the type of routes. Internal, external, NSSA external, or all. If you just put in redistribute OSPF 1, for example, it's only going to import internal routes. If you don't have any external routes, great. But always make sure that you specify those other keywords if you want the other routes included. Another thing you can do specifically is if you're configuring BGP and you're importing these OSPF routes, you can actually use the network prefix mask backdoor command. And what this essentially does is it gives all those essentially OSPF routes a BGP administrative distance of 200, which means OSPF's routes will be preferred. This is just a way of being able to manage connectivity and some of the protocol requirements. Planning for redistribution is essential because so many different things can happen that you didn't intend in redistribution. So understand first whatever the overall picture is, whether you're acquiring a company, whether it's another division, or so forth. Understand the routing protocols that are in use. It's probably a good idea also to know what iOS version is, because sometimes certain commands can take a little bit of a different twist in older versions, for example. Know what the routing domains are, where they are, essentially where the boundary is, and what devices would be involved in redistribution. Which then takes us to the point of know what your border devices are like. Is it a router? Is it a layer 3 switch? How many protocols is it going to be running? You essentially want these devices, because they are border devices, to be on the edge of the domains and essentially be the entry and exit point or points. And essentially this is the spot where redistribution will ultimately take place. Then know all the routes and prefixes in each domain. It can be tedious, it can take a lot of work, but if you have them in your head in advance and on paper, you can actually identify, for example, what routes you know should be there and should not be there. So that type of planning is crucial for success. And then understand what parts of the network actually need access. For instance, traditional hub and spoke environments, which is one of the reasons for the EIGRP stub feature. Stub networks don't need to know about the whole network. All they need to know is how to get back to their particular primary location. And essentially, they can get by with just knowing a basic default route. They may also need to, there may be other parts of the network that only need to know what's within their routing domain. They don't need to know everything. They don't need to know about external routes. Maybe just the BGP or internet exit point, but that may be it. And there may be parts of the network that are restricted. I mean, for instance, in an organization where you have a large number of developers working on something with a lot of security, that may be essentially black-holed in its own way. So they may not need to know about the whole network either. So once you know about networks that don't need to be redistributed, understand your requirements in advance. What routes do need to be redistributed? Determine if you're going to use default metrics, define them in advance and figure out what they need to be. Know the protocols that are required, and then select the devices that you're going to use to perform redistribution. One of the things that's true in life and is equally applicable to networks is to start with the end in mind. Just as an example, when I was a little kid, my middle sister and I would actually do a lot of different mazes, in a lot of those little activity books. And they were a lot of fun, but I would always run into the dead end spots and end up turned around, and I would get frustrated. And what she did consistently is she would start at the end of the maze and then draw her way back to the beginning, and she would never get stuck. And once she told me that and I figured it out, I've never been stuck in a maze since. And the same idea is if you know where you're supposed to end up and then work your way back to the beginning, things end up a lot simpler. So start with defining what your IP routing table should look like in steady state. What route should be there? What route should not be there? In the border routers, the ones that are doing redistribution, what should the routing table look like? Essentially, they should know about everything. Branch location, different story, different sections of the network. Know what information needs to appear in those routing tables and be able to at least write it out at least in some summarized form, because then when you look at the routing table, you know exactly what it's supposed to look like. And if something's not there, then you can adjust so that either a route that shouldn't be there goes away, or a route that's missing ends up in there correctly. Then create a requirements list for your redistribution. Know what a successful project looks like. What are the outcomes? What should it look like and feel like when it's done? How will you know whether you've made a successful redistribution project work? Know what your criteria are. And then try to figure out potential issues. If you think that you might end up having route feedback, for example, try to plan for that. If something might not work correctly because of the kind of protocol that's in use, try to take that into account as well. But use those just as sort of design principles. Start with the end in mind and look at it in this way. So another thing is, just as a general rule of thumb, filter the routes that are being imported into a protocol from being advertised back. And there's two ways to do that. You can use specific mechanisms to deny routes and then permit all others. So you have a series of deny statements identifying all those other routes, and then have a permit any statement at the end of it, for instance in an access list or a prefix list. Or you can use the opposite logic, where you permit only the routes that are needed. So if you know, this is why knowing what the routes should look like in the routing table are important, because then you can actually spell out using a series of permit statements, and then as a result you'll know how to be able to make that work. And you can consider alternative mechanisms if it's appropriate. You may be able to use, for instance, a static route that represents an entire range of addresses and essentially use an aggregated static route. That's a way to necessarily do it without having to use redistribution. Or you can use summarized addresses. For instance, the aggregate address command in BGP. You could actually advertise all of those, or even inject BGP manually by putting it in the IGPs with the network command. But you can also just summarize an aggregate address, and then you don't have to do redistribution, just as an example. So now that we've looked at some general principles about redistribution, sort of the do's and don'ts, and then just a little bit about the protocols, let's actually look at each protocol and specify how to be able to configure and perform the redistribution with that particular protocol. And in this section of the lesson, we're actually just going to consider EIGRP. So what we're going to do is we're actually going to step through the different redistribution scenarios you could encounter, and then how to actually deal with them in the EIGRP environment. So first, let's talk about redistributing connected routes. You can actually use the network command in EIGRP rather than redistribute. For instance, you could actually just have the network command just on a link to an upstream router, and then just do redistribute connected for everything. And you could, but if you do that, it can make things a little more complicated. So it's better to use the network command than to redistribute connected unless there's a specific reason for it. Reason why is you'll end up with an administrative distance of 170 if you redistribute rather than just if it's in the native EIGRP protocol. The other thing is the network command in EIGRP enables both route and interface advertisement and neighbor discovery. It's kind of a 2-for-1. It just simplifies things a lot. So to redistribute connected routes, first you have the desired metric. Remember, it can be a default metric or it can just be using the metric command. But you need to specify all the elements: bandwidth, delay, reliability, load, and MTU. You can actually have a default metric configured, or you can configure the metric as you're redistributing. The second thing you're going to do is actually configure redistribution itself. You've got a couple options. One, if you want to do all of them, you just do redistribute connected, and then you'll pull them all in. And this may be if you don't want to enable EIGRP on those interfaces, but they're necessarily want to be part of the process or maybe part of an external protocol. But redistribute connected just makes it very simple. But if you want to selectively redistribute routes, use a route map. You can start with, for instance, a standard access list with the match IP address command in the route map, and then or the match interface command. For instance, if you wanted to redistribute, say, 3 of the connected interfaces, but not the 4th. For example, let's say that's the one EIGRP is running on, the rest are connected to a different routing domain, just as an example. You could do redistribute connected, reference the route map, and in the route map, match interface, and then list the interfaces. Then you apply the route map using the redistribute connected route map and then whatever the name is. You can obviously also optionally add the metric command to be able to supply a metric. To redistribute static routes, it's very similar. You configure your desired metric, which we already defined. Then when you want to redistribute, you use the redistribute static command if you want all the static routes. For instance, if you only have one static route configured and that's what you run to redistribute, just make it simple. Just redistribute static and you're done. If you have a number of them, this would be the case, for example, perhaps on a border router. Like for instance, router 1, if you remember, actually has a static route pointing to the loopback interfaces of the peers, the BGP peers. So you may have to actually selectively import routes in that case, in which case you'd actually use a route map. Use for instance, a standard access list just because it's simple, using the match IP address command referenced in the route map, or the match interface command if you want to go that route. Then you apply the route map much as we talked about before, and specify the metric keyword optionally. Now, one of the things that may not seem obvious, but if you redistribute from an EIGRP into EIGRP, it's essentially another process. And so there are some different rules that apply and some other considerations to have in place if you're going to do that. So you can redistribute all the routes by just doing redistribute EIGRP on the autonomous system number. In this case, you do not need to configure a default metric because EIGRP to EIGRP, they're essentially speaking the same language. You might want to do it anyway, but it's not required. Then you can obviously selectively import routes using the match IP address, match interface command, and the route map, and then apply that to the routing process using redistribute connected and the route map command, and optionally specify a metric. But EIGRP much simpler. If you're redistributing RIP or BGP, the methodology is similar. Granted, they're very different protocols. They operate completely differently, but the mechanisms within the redistribution process are very similar. You, again, have to configure your desired metric, because if you don't, the routes won't import. So bandwidth delay and so forth. You can use the default metric, you can use a configured metric. When you do redistribution, you will actually use the command redistribute RIP if it's RIP, and BGP and the autonomous system number if you're just importing all the routes from that particular protocol. And again, if for the route map, you create an access list, or you can use match interface and match IP address in the route map. Either way is the case. Then you apply it using redistribute BGP autonomous system number route map name, or redistribute RIP route map name. And optionally, you can use the metric keyword, but you will need to have, if you're doing this with BGP, you must have the autonomous system number 1 configured, number 2 correct. If you use the wrong autonomous system number, nothing will appear. And it's easy sometimes to transpose numbers. I've done it many times as I've configured things. OSPF into EIGRP, some of the same things apply. You have to have your default metric. You can just do importation of all the routes with the redistribute OSPF process ID. And you can use the same procedure that we've been talking about with access lists, route maps, match address, match interface, and so forth. You can optionally use the match type subcommand underneath the route map. And again, the type is internal, external, and so forth. And then you apply that with the redistribute OSPF process ID route map name, and you can override the metric if you like to. But make sure the process ID is in the redistribute statement. So just some key terms to make sure you understand. Redistribution is the process of importing IP routing information from one routing source into another. It's more proper to state it that way than saying another protocol, because you don't think, for instance, example of static routes and connected routes as protocols per se, but they are a routing source. Default metric is a manually configured metric value for a specific routing protocol used for redistributed routes. It is required with EIGRP and RIP. A route map is a tool for more advanced route redistribution. It can use one or more match statements to specify routes to allow or routes to filter. It helps you have more granular work. And incidentally, with route maps, you can also use prefix lists, not just access lists. Match IP address is a route map statement referencing an access list for the purpose of route filtering. Match interface is a route map statement referencing a specific connected interface. It has to be connected. It's typically used for redistributing connected routes. So just 2 elements to this lesson, but a great deal of information. Planning and design for redistribution, tips for success, why you would want to redistribute, and so forth, and configuring redistribution specifically with EIGRP. Our next lesson will actually consider the other protocols as well. Thank you for your attention, and we'll look forward to talking to you again soon.